Alright guys, sorry. I apologize for the very fast cutoff there. Anyway, CSTR, that stands for Continuous Stir Tank Reactor. Okay, so what we're doing here is we first got to know what are the assumptions made when you're dealing with a continuous stir tank reactor. Sorry, I'm still getting used to the screenshots and the screencasts and stuff. Anyway, so the assumptions we made here obviously were N doesn't exist, this doesn't exist, and now it doesn't exist. And that was for a batch reactor. So we need to make some underlying assumptions for this guy. So it's very, and you actually see this written on your test too. They'll say well mixed. That's usually the assumption. So what the heck does that mean? Well, let's do our material balance. In minus out plus gen equals accumulation. Now, we usually deal with, in a batch reactor, where the concentration inside the box is changing. But in the continuous stir tank reactor, if it's well mixed, the concentration of that reactant is constant throughout the whole thing. It's so well mixed, the concentration models as if it doesn't even change. What do I mean? Well, if you have a flow stream in, let's say here, where you have an initial concentration, and out here you got a final concentration, I'm going to call that concentration exit. I think that's what they usually call it in the book. And the concentration exit is the same concentration that's inside the whole thing, right? Because the concentration that's leaving at that outlet that's in contact with the solution is the same concentration everywhere inside the reactor. So that's going to become very important when you're dealing with your reaction rate. So let's say this. We're going to write not CA, that changes with time, just CA exit. So you're going to find that this material balance is very easy because you're not going to be dealing with any derivatives. There's no dCA over dt or anything like that. Also, it's also at steady state, which means accumulation 0. That's steady state assumption. Nothing's changing in the box with respect to time. So you're going to find that these problems are the easiest among all four reactors. Those four reactors, again, are batch, CSTR, PFR, and PBR. Okay, so let's do in minus out plus gen. So basically, the molar flow rate in, we're going to write as FA. The units of FA are moles per second, right? And FAO, or out, will be the same units. So this will be in, I'm sorry, let me write over here, equals in, FA, which still has units of moles per second, equals out. You can even write FA exit if you wanted to. Anyway, gen is going to be equal to, again, it's always never going to change, it's going to be RAVA. It'll change slightly, actually, I take that back. It'll change slightly with PFR, PBR. Okay, let's do the material balance. In minus out plus gen equals 0. Accumulation 0, the steady state assumption. So what we put in for in? Well, it's very simple. The molar flow rate in. The molar flow rate out, which I can even write exit. Right? The generation term, which is RAV, equals 0. Volume is constant, and the reaction rate does not change with position or time. Okay, so for RA, they're going to give you in the problem, it's going to be either negative RAK CA, first order, same ordeal. Second order, mixed, etc. So let's, for this one, we'll just choose this one again. Screw it, I'll choose this one. Okay, so check this out. I'm going to plug in for RA. Let's plug in second order. Well, moving the negative sign, that's a very important thing to keep track of. Let's put negative K CA squared times V equals 0. So in these kind of problems, what they're going to ask you is they're going to ask you to size the reactor. And sizing the reactor basically is another fancy word for solving for volume. Okay? If you want to meet the conditions, what volume do you need? So all the conditions, condition, size. Okay? So let's solve for V. V is going to be equal to, let's add FA exit to this side, minus FAO. These are molar flow rates over negative K CA exit. Sorry. Because that's the concentration inside the reactor. Is the exit concentration due to the assumption we made of well mixed. Okay, so I think we got it. Oh, yeah, sorry. Squared equals, not 0. I'm thinking too fast here. Okay, so let's get rid of the negative sign. How do we do that? Let's flop around the numerator. Basically timesing the top numerator and denominator by -1. FA exit. Carpal tunnel. Squared. Okay. So now if you have these different parameters, you can solve for V. Now here's a little trick. The molar flow rate is equal to the volumetric flow rate times the concentration. So I usually use Q from fluid mechanics for my flow rate, but in here they're going to use little v. So here's what you do. Let's take little v, and that's the volumetric flow rate, times CA naught minus CA exit. And now as you see, you can get everything in terms of concentration. Like this. Okay? So V ends up becoming V CA naught minus CA exit over K CA exit squared. Okay, perfect. And you can split this up and solve for it in different ways to get the volume or the flow rate, and you can move these variables around. So this is basically your equation. Okay, so let's see how much time I got left here. I want to make sure I don't go over. Screw it, I'll do another video now for the PFR, and PBR is the same thing as PFR. Okay, I don't want to keep you guys waiting.